Welcome, I am Omotola Fayomi, and in the next few minutes we are going to completely master nuclear chemistry and radioactivity for your JAMB examination. This is one of the most fascinating topics in all of chemistry, and JAMB tests it consistently every year. Nuclear notation, alpha and beta decay equations, half-life calculations, fission, fusion, and applications of radioactivity. And the wonderful news is this topic has clear logical rules that once learned give you guaranteed marks. We will cover atomic notation, the three types of radiation, nuclear decay equations, half-life calculations, fission, fusion applications, radiation safety, and binding energy, all in these few focus minutes. This is your complete nuclear chemistry revision. Let us go. Before we can discuss radioactivity, we need to master the language of nuclear chemistry, the notation system that describes every nucleus. Every nucleus is described by the symbol A/Z. Then the element symbol X. The top number A is the mass number, the total count of protons and neutrons in the nucleus. The bottom number Z or Z is the atomic number, the count number of proton only. The number of neutrons is simply A minus Z. So for uranium-238, A equals 238, Z equals 92, neutrons is 238 minus 92, which is 146 neutrons. Isotopes here also are atoms of the same element, same Z atomic number or number of protons, but with different numbers of neutrons, giving different mass numbers. Hydrogen has 3 isotopes. Ordinary hydrogen, which is called proton, that's hydrogen 1. Deuterium, that's hydrogen 2 with 1 neutron. And tritium, hydrogen 3 with 2 neutrons. Uranium-238 and 235 are famous isotopes used in nuclear fission. A nuclide is any specific nucleus defined by its A and Z. What about a radioisotope or radionuclide? Is an unstable nuclide that undergoes radioactive decay to release energy and achieve stability. Gives delta plus helium. Check A, that's 238 equals delta A plus 4. So delta A equals 234. Check Z, 92 equals delta Z plus 2. So delta Z equals 90. Element with 90 is thorium, Th. Therefore, uranium-238 gives thorium-234 plus helium 4. Beta decay. A neutron in the nucleus converts to a proton emitting an electron. Carbon-14 decays by beta emission. So carbon-14 gives nitrogen-14 plus beta decay. So check A, 14 equals 14 plus 0. A is unchanged in beta decay. So check Z, 6 equals 7 plus minus 1 equals 6. Z increases by 1 in beta decay. What about gamma emission? Gamma rays are emitted alongside alpha or beta radiation. On their own, gamma rays do not change A or Z. You will see gamma written as a small gamma symbol after the arrow and accompanying another particles. My method for every equation: write what you know. Use conservation laws to find what is unknown. Look up the elements from its atomic number, and this works every single time. Here is your nuclear equation cheat code that solves every single JAMB nuclear equation question in 3 steps. Step 1, identify the decay type. The question will tell you directly alpha decay, beta decay, or gamma emission, or it will give you equation with a missing particle or daughter nucleus. What about step 2? Write down the particles alpha in terms of mass 4 of helium and atomic number 2, beta mass 0 for that electron, atomic number minus 1, positron, that's plus 1, neutron, that's on the screen, proton is also appear on the screen, gamma, no particles, no change. Step 3, subtract from the parent to find the daughter. Alpha parent loses 4A, A loses A equals 4, and Z equals 2. Beta parent loses A equals 0, Z changes by minus 1. Daughter Z equals parent Z plus 1, because beta has Z equals minus 1. So let's practice this question. Radius 226 decay by alpha emission. That's then R 226 array as it appears the equation on the board. So find X. A equals X. A of X equals 226 minus 4. which is equal to 222. Z of x equals 88 minus 2. That's 86. Look up element 86 in your periodic table and you find out that it is radon, Rn. So x equals to 222 radon. So radon 222, write the decay table in the margin of your JAMB answer sheet. The moment the exam begins, it is the first thing you write before answering a single question. There are 3 types of ionizing radiation from radioactive nuclei, and JAMB tests every detail about each one. Their composition, charge, mass, penetrating power, and what stopped them. Alpha radiation is number 1, and alpha particle is identical to helium nucleus. 2 protons and 2 neutrons bound together. Symbol is helium-4 with mass number 4 and atom number 2. Charge is +2, mass 4, atomic mass unit. Alpha particles are the largest and heaviest of the free radiations, which makes them the least penetrating. They are stopped by a sheet of paper or just a few centimeters of air, but their large size makes them the most ionizing. They cause the most damage to molecule they encounter. What about the beta radiation? A beta particle is a high-speed electron ejected from the nucleus, not from the electron shell. It forms when a neutron in the nucleus converts to a proton. That symbol, electron E, O, and -1. Essentially, we need to understand that the charge is -1, mass essentially 0. Beta particles have medium penetration because it can be stopped by about 3 millimeters of aluminum. What about gamma radiation? Gamma radiation or gamma rays are electromagnetic radiation, high energy photons with no mass and no charge. They travel at the speed of light and have the highest penetrating power of all 3. Only thick lead or concrete stop gamma radiation. However, precisely because they interact less with matter, gamma rays are the least ionizing. The key JAMB facts to memorize: penetration and ionization are the opposite order, are in opposite order. Alpha, lowest penetration, highest ionization. Gamma, highest penetration, lowest ionization. Think about it. The more a radiation interacts with matter or ionizes, the more quickly it loses energy and stops. Low penetration. Now, the half-life of a radioactive substance is one of the most beautifully logical concepts in all of science, and it is one of the most frequently tested concepts in JAMB nuclear chemistry. What is the definition of half-life? Half-life, which is T half, is the time taken for exactly half of the radioactive nuclei in a sample to decay. Notice, not all of them, half of them. The pattern is geometric. Start with N0 atoms. After 1 half-life, N0 divided by 2 atoms remain 50%. After 2 half-lives, N0 divided by 4 remains 25%. After 3 half-lives, N0 over 8 remains 12.5%. Each half-life you divide by 2. Again, the mathematical formula captures this perfectly. N is equal to N0 times 1/2 to the power n, where n is the number of half-lives elapsed, and n equals total time divided by the half-life. This formula has 3 beautiful uses. Find the amount remaining, given N0, T half, and total time. Find the half-life, given the initial amount, final amount, and total time. Or find the total time, given half-life and fraction remaining. JAMB tests all 3. The half-life is a constant property of each radioactive isotope. It does not change with temperature, pressure, or chemical state. You cannot speed up or slow down radioactive decay. This is a fundamental law of nature. Now, let us put the half-life formula to work with 3 types of calculation that JAMB regularly set. Master these 3 and you will score every half-life mark. 4 steps method. Step 1, find the number of half-lives n by dividing the total time by T half. Step 2, apply n equals to N0 times half raised to power n. That step 3 is that you can also simply divide by 2 repeatedly n times. This avoid any power calculation. Step 4, check your units, and let's look at this example. Finding remaining mass, 80 grams of phosphorus 32 with half-life 14 days. How much remains after 56 days? N equals to 54 divided by 14, which is equal to 4 half-lives. N equals to 80 and half times n equal to 80 times half raised to power 4, and that's 80 times 1 over 16, which equals to 5 grams. Or step by step, 80 from 80 divide 80 by 2, you will get 40. 40 divided by 2 again, you get 20. From 20 to 10, from 10 to 5 grams. Same answer. Example 2 is that finding the half-life a sample decays from 200 grams to 12.5 grams in 60 hours. How many halvings does it take? 200 to 100? Yes, half. Half of 100 is 50. Half of 50 is 25. Half of 25 is 12.5. That's 4 steps. So the 4 half-lives in 60 hours is T half equals 60 divided by 4, which is 15 hours. There are the third example, finding total time. T half equals to 8 days. How long until only 1 over 16 of the original remains? So half raised to power n equals to 1 over 16 and equals to half raised to power 4. So n equals to 4. The total time equals 4 times 8 equals to 32 days. Step by step division method. From 80 to 40, from 40 to 20, from 20 to 10 and 5 always works and requires no calculator. Use it in JAMB when no calculator is allowed. Count the arrows, multiply by T half. Now let's look at nuclear fission, which is one of the most dramatic and consequential discovery in human history, and it appears in JAMB every year. Fission occurs when a heavy nucleus like uranium-235 is struck by a slow thermal neutron. The nucleus becomes unstable and split into 2 smaller daughter nuclei, releasing 2 to 3 more neutrons and enormous amount of energy. The classic JAMB equation, uranium-235 plus 1 neutron gives krypton-90 plus barium-143 plus 3 neutron plus energy. Let us verify the conservation laws. Mass number, 235 plus 1 equals to 236. 90 plus 143 plus 3 equals to 236. Check. Atomic number, 92 plus 36 equals 36 plus 56 equals 0. That's 92. Check. Always verify both. The chain reaction now is what makes fission so powerful. Each fission releases 2 to 3 neutrons. Each of those neutrons can trigger another fission, releasing more neutrons, which triggers more fission. Exponential multiplication of reaction. Uncontrolled chain reaction, the energy is released almost instantaneously, and this is the principle of atomic bomb. Fortunately, controlled chain reaction. Control rods made of boron and cadmium absorb the excess neutron, keeping the chain reaction at a steady, manageable rate. This is the principle of nuclear power reactor. The moderator, that's water or graphite, slows the neutron down to the right speed to sustain fission. The coolant removes the heat produced. Critical mass is the minimum amount of fissile material needed to sustain a chain reaction. Below critical mass, too many neutrons escape before hitting another nucleus. The reaction dies out. If fission is the power of splitting atoms, fusion is the power that keeps the sun burning for billions of years, and it is the ultimate energy dream of humanity. Nuclear fusion occurs when 2 light nuclei combine. They fuse together to form a heavier, more stable nucleus, releasing tremendous energy. The most promising fusion reaction involves hydrogen isotope, deuterium, that's the hydrogen 2, and deuterium. Fusion equation, that's the hydrogen 2, deuterium plus deuterium gives tritium plus hydrogen 2, that's the deuterium plus deuterium gives tritium plus neutron plus energy. However, the easier route is that hydrogen 2 plus hydrogen 3 gives helium 4 plus neutron plus energy. The helium nucleus produced is the incredibly stable alpha particle. Radioactivity is not only a natural phenomenon, it is an incredibly useful tool that saves lives and advances science. JAMB tests the application of radioactivity consistently. Medical applications, gamma radiation from cobalt-60 is used in cancer therapy, and high-energy gamma rays are focused on tumor cells, destroying them. These beams are aimed from multiple angles to minimize damage to surrounding healthy tissue. The medical tracers. Radioactive iodine-131 is swallowed or injected and concentrates in thyroid gland because the thyroid uses iodine. A gamma camera then detects the radiation from outside the body to image the thyroid without surgery. Titanium 99M is the most widely used medical radioisotope worldwide. It is short half-life 6 hours means it decays quickly, minimizing patient exposure. Carbon-14 dating. While alive, organisms continuously exchange carbon with their environment. When they die, the carbon-14 in their body starts decaying with a half-life of 5,730 years. By measuring how much carbon-14 remains, scientists can calculate how long ago the organism died. Reliable to about 50,000 years. Thickness gauges. Beta particles have just the right penetrating power to be affected by thin materials like paper, plastic film, and aluminum foil. As the material gets thicker, fewer beta particles pass through. This is used to automatically control thickness in manufacturing. Smoke detectors. A tiny amount of americium-241 as alpha emitter ionizes the air in the detector chamber, creating a small current. When smoke particles enter, they absorb the alpha particles, reducing the current, triggering the alarm. Understanding radiation hazard is not only important for JAMB, it is important for life. Ionizing radiation has the energy to knock electrons out of atoms, damaging molecules, including the DNA in our cells. External hazard. Gamma radiation is the most dangerous externally because it penetrates deep into the body and reaches internal organs. Beta radiation can cause skin burns. Alpha particles are not dangerous externally because they are stopped by the skin. Internal hazard. The situation reverses completely when radiation sources are ingested or inhaled. Alpha particles, being the most heavily ionizing, are most dangerous internally. They cause severe damage to the surrounding tissue while unable to escape the body. What about radiation protection? It follows three principles. Time. The less time spent near a source, the less dose received. But of distance, the key formula. Radiation intensity is inversely proportional to the square of the distance. Double the distance. Reduce intensity to 1/4. What about shielding? Appropriate materials. Paper for alpha, aluminum for beta, lead or thick concrete for gamma. Background radiation is the low-level radiation we all receive continuously from the natural sources. Radon gas seeping from rock and soil, the biggest source. cosmic ray from the space, radioactive material or minerals in building materials, and even tiny amount of radioactive potassium floating in food. The gigamolar tube detects ionizing radiation. The count rate must be concreted for background radiation. Corrected count rate equals measured count rate minus background radiation. What about the concept of binding energy, which connects nuclear chemistry directly to Einstein's famous equation E is equal to mc squared, and reveals why both fission and fusion release such incredible amount of energy? Here is the beautiful insight. When you measure the actual mass of an atomic nucleus, it is less than the sum of the mass of its individual proton and neutron if they were separated, This missing mass is called mass defect, which symbolized by as delta n. Whereas, does this mass goal extend equation answers it perfectly? E is equal to mc squared. The missing mass has been converted into binding energy, which is the energy that holds the nucleus together. This is also the energy that would be needed to completely break nucleus apart into individual nuclei. The binding energy per nucleon, that's the binding energy divided by the number of nuclei, tells us the stability of nucleus. While both fusion and fission release energy, nuclei heavier than iron, like uranium, can gain stability by splitting as fusion into smaller nuclei closer to iron inside. Nuclei lighter than iron, like hydrogen, can gain stability by joining fusion into larger nuclei closer to iron. In both cases, the product are more stable and the energy difference is released. Here is your complete nuclear chemistry and radioactivity cheat code. Every key rule in one consolidated exam-ready summary. Nuclear notation: A over Z gives the mass number total as total nucleon, and the atomic number proton. Neutrons is equal to A minus Z. Radiation rules: alpha losses 4 from A and 2 from Z. Beta leaves A unchanged but increases Z by 1. Gamma leaves both unchanged. Penetration: alpha less than beta less than gamma. Ionization: opposite: alpha greater than beta greater than gamma. Half-life: n equals n naught times 1/2 to the power n, where n equals time divided by t half. Step-by-step method, just keep dividing by 2, work every time. Calculator: fission heavy nuclei split, uranium 235 plus neutron gives 2 daughter nuclei plus more neutrons plus energy. Chain reaction: nuclear power plants, controlled fission, fusion, light nuclei join, hydrogen isotope fuse to give helium plus neutron plus energy. The sun is a fission reactor. There's a particular agency working on making it work on Earth. Carbon-14 half-life is equal to 5,730 years. Exactly. E equals to mc squared. 6 final power tips covering most subtle and most frequently tested details in JAMB nuclear chemistry. 1. In beta minus decay, a neutron converts to proton. The atomic number increases by 1. The daughter element is one position to the right in periodic table. Students sometimes think Z decreases. It does not. The electron emitted as Z in equals -1. So parent Z and daughter Z plus -1 means the daughter Z equals parent Z plus 1. Always increase. 2. Always increase. 2. Alpha is the most dangerous internally, most ionizing, so it damages more cells per centimeter inside the body. But gamma is the most dangerous externally. It penetrates through the body wall to reach organs, contact matters, for which is more dangerous. 3. In any nuclear equation, both mass number and atomic number must balance. If you only check one and you have 50% chance of error, always check both before choosing an answer. No temperature change, no physical process, can change half-life of a radioactive element. The rate of decay is determined purely by the nucleus and is a constant of nature. 5. Radioactive decay is fundamentally random and spontaneous. You cannot predict which specific nucleus will decay at what moment. You can only predict the rate at which a large population of nuclei will decay, which is where the half-life comes in. 6. Nuclear reactor components for JAMB, the fuel rods, uranium-235 provide the fissile material. The moderator water or graphite slows neutron to the right speed. Control rods as boron or cadmium absorb excess neutron to control power level. The coolant, water, CO2 or liquid sodium remove heat to generate steam for turbine. Now, two bonus concepts that appears in higher level JAMB question. The uranium decay series, uranium-235 does not decay directly to a stable product. It undergoes a long series of alpha and beta decay, producing 14 different nuclei along the way before finally reaching stable lead-206. This series involves 8 alpha decays and 6 beta decays. The counting tricks for decay series is that if a parent nucleus undergo a unknown number of alpha and beta decays to reach a daughter, set up two simultaneous equations, mass equation. 238 minus 4a equals 206 gives a equals 8. Then 92 minus 16 plus b equals 82 gives b equals 6. Beta 8 alpha 6 beta decays. What about artificial transmutation? In 1919, Ernest Rutherford achieved the first ever artificial nuclear reaction. He bombarded nitrogen-14 with alpha particles and produced oxygen-17 and a proton. This was the first time one element was artificially converted to another. Bombarding uranium-238 with neutron can produce plutonium-239 through a series of beta decay. This is how nuclear reactors produce plutonium as a byproduct. Outstanding! You have just completed this few minutes masterclass in nuclear chemistry and radioactivity. You now know nuclear notation and isotopes, the 3 types of radiation, alpha, beta, gamma, with all their properties. How to write and balance nuclear decay equation, how to perform all 3 of half-life calculations using n equal to n naught times half raised to the power n. The chain reaction in nuclear fission with uranium-235, how nuclear fusion powers the sun and how and who the promise of future energy, the application of radioactivity in medicine and science, including carbon-14 dating, radiation hazard, and 3 principles of binding energy, and why iron 56 is the most stable nucleus, and how to count alpha and beta decay in a decay series. That is the complete JAMB nuclear chemistry syllabus. If this revision helped you today, and I know it has, please like this video right now, share it with every chemistry student you know who is writing JAMB, and subscribe to this particular channel for more rapid revision walkthrough on every topic in JAMB chemistry. Comment below which concept clicked most clearly for you. The half-life calculation, the decay equation, method, or difference between fusion and fusion. I read every single comment. You are not just born to pass JAMB, you are born to excel in chemistry, in career, in your faith, and in your life. So we say God bless you richly. Your nuclear knowledge is fully charged. Go and get that A grade. I will see you in the next video. More. Cheers.